lecture, which will be given by Maruf Dhali. Maruf has a Master of Science degree from Edinburgh and is a computer science and artificial intelligence PhD researcher in this same ERC project. And he works in the Department of Artificial Intelligence of the University of Groningen, together with his first supervisor, Professor Lambert Schoonmaker. One of his great qualities, since I was mentioning qualities of Naden, I should also mention the qualities of Maruf, is, and that is only a quality that I've been able to see, he may have many more, of course, but one of his great qualities is his patience and his didactic skills in explaining computer intelligence, computer science to humanities scholars. After Maruf has explained it, you have the feeling that you understand at least half of what is going on. So I hope that Maruf will give you the same feeling when you listen to him, and some of you may even understand much more than I ever do. So Maruf, the floor is yours.
Thank you very much, Ivert. Thank you for the nice introduction. It's a bit too short of a time, but I'll try to make you understand full this time. I'll try. Okay. Here I start. So I am a PhD candidate in this project, and I will briefly explain all the small technical parts that we use in this project. So I will start with the goal. So the goal is the same with the whole project, also at the AI part, to find the two questions, who and when, for this DCS course manuscript. Now, to work with, we work with the digital images. So we have two sources of digital images, one from the IAA and another from the Brill collection. Now, the IA images, we also get them into multispectral bands. So for each of the fragment images, you have different spectral bands, and these bands are important, will come later in my presentation, that some bands are good in ink and background separation, some are good in really seeing the ink, some are really seeing only the background. Now, where do we put our data in? So for the data storage and putting the data and processing, we use the Monk system. It is also built in-house in the AI department from Lambert Schoonmaker starting from 2008. And it is one of the most diverse collection of handwriting manuscripts. And it is also running 24/7 machine learning. And it has a really massive data storage and at the same time performance. Sorry for the noise. So also in this Monk system, you can have a web interface where can people go in like any humanities scholar, and they can really select a part of it to show that, okay, this part is from this fragment. So it is kind of like labeling the data. So we take advantage also of this procedure where we ask scholars to label the data, and on the background, we get the XML data as our label. So let's start with the processing itself. So how the computer-aided techniques work. So the first thing first, we work with the images. And whenever we work with the images, for these DCSQL things, what we want is we want the characters to be extracted, because we are more focused on what is written there, what is the ink, how people are writing things, to answer both the question, who and when. Now, to do that, one of the things you see that this is the digital image, and one of the really unit elementary component of a digital image is the pixel. So if you go to the pixel level of this image, even for this nice image, what you see is the separation between the ink pixel and the background pixel is not that, how to say, contrastful, or it's not that easy to find when you go to the pixel level. Even for human eyes, you see the big image, you read the characters. But when you go to pixel level, you don't know which pixel is background, which is the ink, and when the separation is coming. Then think about all the different things we have in the DCSQL collection. So it makes it a really complicated and difficult problem, all in all. Then we have all these different kind of traditional techniques, like traditional computer vision techniques, where people have set pieces of programs to binarize these images. So in here, you see that in both the rows, the second column is how a human is labeling the characters. So how a human sees the characters. It's really amazing that human knows where the characters are and it sees and it's read. But then the other three, Osuni, Black, and Savola, they're really successful techniques to character extraction. We call them binarization. So binarization means that making ink pixel black and everything else that's white. So we want to binarize things, but with also Niblex or Vola, it's not that easy. They're kind of binarizing some of the characters, but at the same time, they're also extracting a lot of color calibrator scales and other things that we don't want. So where is the problem? So I'll just step back and tell you something about a different thing. Where are we actually approaching? So let's think about this. That this is a character and it's a 3. So it's super easy to recognize that it's a 3. And then if you go to pixel level, it's super easy. So you can write a program like whenever you see a 0, that is background, and whenever you see something from higher than 0, it's 1. Then think about all the different kind of 3 that you're writing at different time of the day. And then, okay, you start writing different programs, and think about thousands of millions of different kind of 3 you can write. And then this becomes a really complicated problem to write a specific program. So this is where maybe we can go into AI. So we can go into the point that can machine really think. So what is AI? In short, I'll be really vague. So it is also making computers mimic how we work. I will give you a brief example. So when I'm talking about traditional programming of software, so it is like the things are predetermined. It can be really complicated. It can be going into space with a NASA spacecraft that you program each of things. You write hundreds of thousands of lines of code as an algorithm. But AI is a bit different. It is like where you have a learned component, like how a human is learning. And then it also takes into account of decision making, seeing. Then you can say that it's vague, I know, but you can say that it is the artificial intelligence based system is experiencing what is going on like a human, but in a mathematical way. So how you design them? So basically you design them mostly how the biological nervous system works. So basically you make a common mathematical model of the biological neuron of a human brain, and then you consider this as a node and you make it a layers of node like the nervous system. So in a typical neural network, so AI is not only neural network, but it is commonly used term. So in a typical neural network, you have these input nodes, these hidden layers, output nodes, connections, and a lot of other functions. So you have layers of mathematical models, algorithms together to solve this small problem, recognizing 3 or recognizing 2. Then we make it a bit more, how to say, useful for our case and more broader. So we do an advanced deep learning based ink-based separation method. So it can do ink and background separation. And it also has this high ability to learn a complex nonlinear output input, in our cases, a normal image to a binarized image. So we build this network, the binet, which has, you see, all these layers. And from a normal image, it just works. You give a normal image, in output, it gives you a binarized image. That's how it works. Then we also take advantage of the multispectral images that we get from IAA. We fuse those images and we make a pseudo-synthetic color image. Then why do we make it? Because you can see in this image that the color or the color spectrum image on the top left, and then the greenish pseudo-synthetic color image on the bottom, you see that the ink and background separation is much more clear in the bottom image than the top image. So we kind of take advantage of also these, and then binarize all kind of images. So just to show you a bit of results. So in every kind of images, you see that we go into a simple ballpark. The original images might be different, but when you go to the ink space, you work with the ink. So if you're classifying different manuscripts, you don't want to classify them for wrong reason, how the background is looking like, rather than you really want to work on the ink itself. Now, let's say of all these 4 kind of images, they look different when you are in the grayscale space, but when you go to the ink, okay, you are in the same ballpark. Then you can have some calculation. Now you are in a battlefield in a way. So you have all these kind of characters, or also for the 1Q Isaiah, that we get the grayscale images, we get a bit binarization, we clean it, and we have these nice characters. After we have these nice characters, this is the first point of all the calculation that begins. So everything I talked till now is a pre-processing step. Once this is done, we have the characters. Then we want to find out what are the features, what are the attributes of this character. So we do textural based feature extraction, like we calculate different kind of things for each of the characters. Then, for example, this is a picture of hinge where we're doing like the joint probability distribution over the whole manuscript. Then we also have cold, and then we try to measure the cloud of the line distribution. And on top of these textural things, we can also go to the allographic space where we work with the whole character shapes. So then we do it in a self-organizing map. And we also work with the fragmented character shapes. And why from whole to fragmented? Because a lot of time we see that the change in style or change in character shapes are more easily distinguishable in the small part of characters rather than the whole character itself. And that's why we do also the fragments. So these are different kind of features. Once we have the features calculated, the features are multidimensional. We reduce them into a three-dimensional space to make a plot, like a three-dimensional plot, so that it's easy to see where the manuscripts are, how far they are from each other. Then for the example of 1Q Isaiah, when you plot them, then you also want to see if there is a cluster or not, if two, 3 or 4 clusters are there or not. So it's an easy way to do writer identification in a way. So once we do writer identification, we also do a lot of secondary analysis, a lot of statistical tests to see what we did in the feature calculation and plotting is really true or not. So it's kind of like a double test, a double confirmation. And we do a lot of different kind of tests, t-test, f-test, logistic curve fitting, and things like that. I'll not go into the details, I'm just giving a quick overview. And then we also present tertiary analysis, like a visual inspection of what the computer is seeing. Is it also visible in a human space? Like in your eye, can you see also these small differences or not? So this is on top of all the analysis that we did before, like feature extraction, then plotting, and then statistical analysis. This is a third level of analysis. We also presented it into our 1Q Isaiah paper. Then I come into the new topic, the style development. So here, Mladen already explained that we actually have 3 information sources, the radiocarbon dating, and then the AI methods, and the paleographic knowledge. Now, what we can already do inside Monk is to predict the periods. So here you see that by knowing the common looking or general shape of either Hasmonean or Herodian or archaic period, we can already estimate, given any document, what is the period of that. But do you want to really settle down there? No, not really. So you want to go a bit further. We want to know a more precise date. So we don't want to know just the periods, we want to know the dates. To go there, we are working with several master students, then Lambert, Schumacher, me, a lot of people are in AI, are involved in there. So one of the things to do a precision dating is an approach that was already, an article from Sheng, from one of our postdoc, has shown that with MPS dataset, you can have a really precise dating. Well, now, can we do that for this syscall? Not really, because we don't have this kind of nicely, uniformly balanced and distributed dataset for this syscall. What we have is only this thing, the Mare-Shostakon, which is 176 BC, and that is the only thing that is dated within this syscall period in the middle. So we cannot really do things that is commonly done for handwriting recognition dating. So we go to the radiocarbon dates. So we have the radiocarbon dates, and for each of the radiocarbon dates, we also have a manuscript. So we tag the manuscript with the date that is coming from the radiocarbon dating. Then we have several approaches. So one of our master students with us, we are working that artificial neural network that is learned on the character shape, and based on the character shape, it is trying to predict what are the dates. And then you have this encoder decoder kind of network, artificial neural network. It is trained to mimic the characters. And once it learns the character, from the learned character, we take out the decoder part, we put a fully connected layer, then we train it on the C14. And we see that it does have a really hard time in predicting the dates for the undated manuscripts. Why? Because one of the key issues with neural network is it always needs a lot of data to be trained, because it mostly knows nothing. And if we want to do transfer learning, take a pre-trained network and then train it, we also see difficulty because of dissimilarity of different kind of scripts, handwriting, and data set. So we are also doing a different approach. So we do feature calculation like we do in writer identification, and then we do a bit of computer modeling based analysis to estimate the undated manuscripts. So just to give you an example of one QI there. So this is column 3, random column 3, 13, 29, and 44. So for each of the columns, we get a prediction. Then we kind of, for all the 54 columns, we try to see what are the predictions. So it is kind of taking for the whole things together. And then we commonly see that this is what the predictions look like for the 1QI there. And I'm not an expert, but just to see the curve, I know where the date can be. And it kind of shows that a probable date can be -100 to -200, and it has different ups and downs peaks. And then we present it to the humanities paleographer, and then we also explain them how to read this curve, and thus they can decide on what is a predicted date for this given manuscript. Here, one key thing is that the blue curve that you see is the average of all the means, and all the red bars is the error bars. Maybe I'll not go into the details, but if you have more questions, you can always reach me with this. And we are, this is still new, and we are still developing it. And hopefully in the coming months, we'll be publishing more about it. Now to give another interesting example, because Mladen was already showing this, that the Nash papyri. So we use our model, and this is just to boost a bit that you see that when you pass it to the BINET network, it directly binarizes the characters and it doesn't get bothered with all the other things in the picture. Now, to make our life more complicated, but also to challenge our system itself, we split the Nash papyri into 4 different parts, like first 8 lines, then next 7 lines like this. And then, for example, in the first 8 lines, we also added noise and put them together. So it looks like separate documents. Thus, from one Nash papyri, we came out with 44 different images. And then we try to predict them. And then we port all these 44 images separately and try to see what is a common prediction for all these 44 images. And also for this, you see that there is a small hump in +50 CE, but it also comes with a lot of error. And then you have another hump, which is from -150 to -200. And there you don't see that many error anymore. So this is how we present the predictions. Now to conclude. So we have a system now that works robust in a consistent way. Is it perfect? If you ask me, I would say that the system is working perfect. We still have issues of how the system is trained. And now the system is trained on the radiocarbon data. And we have the amount of radiocarbon data we have. This is the anchor of everything. So if in future, if there is more internally dated manuscript that is getting excavated or something new is coming, you can always feed it into the system and have your results more refined. So this is a starting point for the future of dating, I would say. Thank you, everyone.
Thank you, Maruf, also for the time. So we have ample opportunity for questions. At the moment, I see 2 questions in the Q&A box, which I can see as the chair. And I forgot how to do it, but I will just read the question of Jonathan. Are you a panelist or an attendee? I will read out Jonathan's question. Jonathan Adler asks, Maruf mentioned the ostracon for Malaysia internally dated to 176 BCE, but how valuable is this for determining paleographic dates in the Dead Sea Scrolls? Apart from the fact that it's written on pottery, as opposed to skin, the writer was presumably an Idumean, not a Judean. Now, it could be a question for Mladen or for Maruf. I just look at both of you. Who wants to answer this question?
maybe Maruf, I start first with say the cultural part, and you can maybe share a bit about what weight the Maresh Ostrakon gets and how it's balanced in relation to the C14 data, so it's not too heavy or too strong. In terms of being Jewish or Edomian, first that part, I think what we need to look at here is the style of writing, and not necessarily distinguish between different groups of people that we see, but there's a similarity in the way that the script is written, and it is shared apparently across. So that in itself, I would not see as a hindrance. Now, then the part of the material on which it is written, that in this case, I think is also not such a big issue because of the binarization that was made. But maybe Maruf can say a bit more on that part of the difference between the background being different and then the image processing.
Yeah, so this is also one of the advantage of doing binarization, so that you don't start clustering things for wrong reason. So once it is binarized, the background doesn't really matter. But also I can understand if something is written on pottery and then something is written on leather, how you compare them. So one of the good news and the bad news at the same time is where the Maresh Ostrakon is also where a lot of our radiocarbon data, the dates are. So I tried to do it, and then we also tried to do it with several students as well, to give Maresh Ostrakon in the training set, having it there and also removing it there. And we see that the change is not that much. So it is not really changing anything in a way. The reason for that is maybe the handwriting of the Maresh Ostrakon is similar to many of the radiocarbon dated manuscripts, so that it is kind of balanced out. And the other thing is that it's just a one-off instance in the middle, like 176 BCE. So in a training of several other manuscripts, it is not strong enough to do something drastical in and of itself. So that would be my explanation.
Yeah, maybe to add to this, Shira Feigenbaum is asking what was the training data. As I said in my paper, that's 25 C14 dated samples and then manuscripts, and 23 internally dated manuscripts, which are mainly on the outer ends of the time spectrum.
Yeah, but also one thing is that each of the manuscript has several fragments. So if you talk about image-wise, we are using 96 images.
Yeah.
Okay. I see a very technical question by Gideon Joffe, and he can pose the question directly to Maruf, I think. Gideon, go ahead.
Hello, thank you very much. I hope you can hear me well. Well, I just had a technical question about the plots. Time
it's the
versus
sigmas, actually.
So each orange curve is 1 sigma, which means that even in the case of the latter numbers, the CE dates, their statistical uncertainty is on the order of like 1 or 2 sigma. Am I correct?
Yeah, exactly. Yeah.
Okay, thank you.
I see another question by Steve. I'm not sure whether he can ask directly. I'll just read a question. What type of neural network are you using for the binarization network? Are you using any pre or post processing, and what sort of hyperparameters are you using?
Yeah, so for the neural network, we are using a variant of UNet kind of network. So it's a mixture of UNet with a bit of half of the GAN. So UNet and GAN together. We have all the details in our BiNet paper with all the hyperparameters. For the BiNet network, we are not using any kind of pre or post processing for the DCS calls. So for all the DCS calls, they go as it is directly. So the network takes, for example, for the fragment images, 3 different band images. It does, the fusion. So you get a pseudo color image, and then it passes to the network, and then you get the output. but we are also trying with different kind of other images, historical images. For example, the Nash, you saw that the Nash goes directly as it is. But then again, the Nash paper, we have the color image, you also have the grayscale images. And then for the grayscale images, I got from the infrared image from the Cambridge Library website. When I pass it directly to the network suffers a bit. Then I try to improve the curve of the network. Sorry, improve the curve of the image. So it really depends. So if you are using the same network for some other purposes, then either you do a bit of update like a transfer learning on your data, or you have to do a bit of pre-processing. But for the DSQL, we don't do any sort of pre-processing. I hope that answers. Yeah.
Steve, I hope it's enough. A comment by Nahum, who says, Nahum Deshevis, not necessarily requiring an answer, but stating that the dating graphs all show noticeable valleys with low probability, which presumably is attributable to insufficient data, but is disconcerting nonetheless. Nahum said it's just a comment, not necessarily an answer. If there's a short answer, you can give it. Otherwise, I have more questions to you.
No, but I completely agree with Nahum. We don't have that many data that the plot would be really nice and perfect. So everything, all the, let's say, bit of anomalies you see here and there is mostly because of insufficient data and also how the data looks like.
Nahum, that's okay with you?
Yeah. But thank you very much for the comment. Yeah.
Okay. Daniel Stöckel requested whether he could come back to the question by Jonathan. Daniel, can you ask it directly, succinctly?
Sure. Thanks, Albert. Jonathan asked, this question is probably more to Mladen. So the Marisha Ostrakon was written by Idumeans, which is not exactly the same as the Qumran community. And it's on a curved Ostrakon, which is not the same type of support, writing support. So it's harder to infer from that. And I've got two other questions, but I don't know whether I should ask them already also, Albert.
Briefly, yes. So Mladen can choose.
So more to Maruf. So the 50 pegs, half of which are outside of the narrow sample, meaning Qumran, is relatively little data, I think. And because it's ranges rather than precise dates, also the resulting dates are extremely wide. Are these dates based on 1 sigma or on 2 sigma? That is what I didn't understand. And for the binarization, to what extent does different skin or different parchment impact different binarization, so the outcome? Thank you.
Thank you very much, Daniel. It's nice to see you. So I'll answer the last question first. So for the binarization, during the training process, we did intentionally put both the papyrus and the parchment. So in our binarization training process, altogether we had, if I remember correctly, it was a couple of years ago, we had 40 images, and out of those 40, we have 32 parchment and 8 papyrus. So the network does flawlessly with both papyrus and parchment. The one important thing with papyrus is that the papyrus images itself, even now, they are quite damaged and broken in character. And also, like when you write them, how the ink deposition is happening on the fibers, it has also a bit of issues itself. So the papyrus binarization is never as good as parchment. That is true, but with the binet, the parchment, so the papyrus binarization is what we are getting is still the best we can get out of any technique that we have now. And you also see it with the Nash. And for the first question, the sigma, so we are using this radiocarbon dates, and Mladen was saying that we made a choice of how much to take for each of the C14 dates. And then if Mladen wants to speak further on this, that how we made the choice, and after making the choice, that data goes directly into the system. If Mladen wants to elaborate a bit on the choice, yeah.
Yeah, I mean, the first and foremost, we use the 2 sigma date ranges from the C14. So we don't make any choices in that respect. What we mean is that, as you could see with the graphs, because of the calibration curve, for a number of manuscripts, you will find 2 possibilities, one say in the 4th century and another say in the 2nd century BCE. And there we made a choice, and we explain it, so it's all open and transparent, that we ignore the earliest ones based on the implausibility of it, of the writing style you find in those documents that contradict the type of writing style that we find in internally dated manuscripts from Elephantine a bit earlier, 5th century, but from 4th century, Wadi Dalieh and Bactrian material from the Khalili collection, for example. So I hope that answers the question. There is no, it's a simply 2 sigma also, the data from the C14. And then on the first questions again on Maresha, yeah, of course, I mean, Idumean is not the same as Qumran, but we do not limit ourselves to Qumran only. We also take into account other manuscript find places from the Judean desert and also outside of it. So we look with a broad view to the development of the writing style, and that is not new, of course, in our fields. I mean, Cross, of course, also looked at the Nash papyrus, but then when the Maresha Ostrakon was known in his 2003 update of his 1961 article, he also draws that into account. As to the question on the surface being a bit more concave and things like that, I think Maruf can say a bit more on that, how we managed the image processing there.
Yeah, Maresha Ostrakon itself was a bit difficult one. And also for, yeah, how to say this, 1Q Isaiah, we also did one thing after the binarization. We did a bit of stretching correction or like deformation correction. We are really careful with that. And just to see if the stretching or deformation correction did have any issues, we did try with the raw images and also the stretching or the deformation or geometric anomaly correction images together, and also with added noise. Once we see that there is not that much of a difference, then we use the corrected image. I hope this answers quickly.
Thank you very much to both of you.
Thank you.
Thank you, Maruf. Thank you for all the ones who posed questions, for keeping exactly to the time so we can move on to our next speaker.